Okay. Thank you very much, and thanks for the invitation. It feels like being a party crasher, being only one of two experimentalists here. But I hope that in the course of the talk I can show you that there's a chance that experiments actually can implement those very interesting concepts, and the gap actually gets smaller and smaller, basically, between theory and computer scientist concepts and ideas and what actually can be done in the laboratory. As you can see from the title, we work with photons, and I would like to use a few slides to make advertisement that there's a reason why we still work with photons, and I'm a fan of those nice little guys. First of all, it's very nice to implement qubit 0 and 1 states by using the polarization degree of freedom. You see basically the Bloch sphere is the same as the polarization sphere. You can address that very nicely with a simple plate, so it's actually undergrads can do it after a 5-minute introduction to go to any point on a Bloch sphere. We can make measurements very nice by splitting polarization, one or the other on a cube like here. We can split them into different paths. So you see this, it's a very accessible qubit with respect to many other systems. The more tricky part is to get entanglement, and now we use for more than 20 years the same way to get entangled photons because it's still the best option out there. What we do is we use a nonlinear crystal where basically one photon, one blue photon goes through, and there's a small chance that this blue photon is converted into 2 red. It has to, of course, obey energy conservation, so 1 blue is the same as 2 red in terms of energy, and of course momentum conservation. If you take the right crystal, they're orthogonally polarized. You see there's one polarization cone, here's the other cone. Now you see a picture. Basically, you look at the crystal when the photons come out. What's the tricky part? The tricky part is you should get the same frequency guys, let's say the green ones. This is one polarization state, here's the other state. And if you take photons from the cross sections, then you know they have to be different, but you don't know basically which one belongs to which cone. So you get almost perfectly entangled states with up to 99.9% fidelity. To explain in a movie what I just said, now we have a movie here with a CCD camera where you look at the crystal, the laser shoots in your eye, and if you tilt the crystal, you change the properties in such a way that suddenly you see that this down conversion starts happening. And if you tilt further on, you see how the cones appear, and then when they start to overlap, you would stop there to catch the entangled photons. Since we like this movie because it's so nice to show how it goes, let me show it here. Basically, you see this down converted photons, H polarized, V polarized. You tilt further on, and you see at some point they start to overlap. You would stop here and catch photons from this small point here and there to get your nice entangled photon pairs for whatever you would like to do, CHS, H-test, quantum computations, and so on.
So what do you mean by catch photons from here and there?
Sorry, basically there's a crystal shining light into your eyes. There's a single photon, so really like the smallest amount of light. And you would basically put a fiber or some coupler there to catch just from this cross section, okay? Otherwise, they're not entangled, because only when you get photons from these cross sections here, okay, you're able to get entanglement, because you know they have to be orthogonal, but you don't know which way. Independent.
So you actually have a fiber that's physically located at that point.
A lens and a fiber, and that's the tricky part. So the hard part is to get this arrangement that you have this situation happening, and you get them right from there. Okay.
So how big? What's the scale there?
The crystal.
On the picture, the scale.
That's basically a few hundred microns, like 0.5 millimeters. So, but this one is like you couple it into 5 micron fiber. So well, it takes some experience, but people nowadays know how to do it. Okay. Since I heard from Dorothy, it's a computer scientist workshop, we should not spend too much into experiments. I hope I can go slowly towards the experiments. For wrapping them up, photons, I think in my eyes, a neat system that allows to combine basically everything that's out there with quantum fun. It basically can cover, of course, foundational tests, which are done for many years now, violation of Bell inequalities and so on. They're the natural choice for communication purposes because they fly at the speed of light. Of course, they're also natural choice for metrology applications, where it can also achieve enhancement by using quantum states of light. And now for roughly 10, 12 years, people have realized there's a scalable approach in principle where you can use photonic systems for making quantum computations. How do you make your gate operations? Basically by measuring extra photons, as shown here, which process your input states through the computation. The thing that I've not realized until I met Elham Jones on is actually that you also can combine them in different directions, which means, for example, you can combine communication and computation purposes because they're mobile. So So you can use mobility as a key feature for starting like cloud computing or delegated computations. So until I met these guys, my understanding was basically like this of the comic about cloud computing. So just brief ideas about Gmail and Yahoo. But then when I met the first time Element workshop, I was fascinated by this blind quantum computation. And then very soon afterwards, we had the first meeting with the theoreticians who proposed this theory model here in Edinburgh. There's M. Broadbent, L.M. Kashefi, and Joe Fitzsimmons. They basically had the first interaction between experimentalists and computer scientist theoreticians. It took some drinks, actually, to realize, yes, with a few photons in your hand, you actually can do something. And it turned out it was like a 3-year project until we got the final result. And it was a very interesting road where both sides, I guess, could learn a lot, at least from my side. It was very interesting to see how things work from the other side of the thing. Okay, thanks to Joe, I can make this rather brief. So the idea of blind quantum computing is to combine cryptography, the benefits from quantum cryptography and quantum computing. You can also map this in this kind of delegated computation that is as a client sending something, just tiny quantum information to computer. He makes the entanglement, he makes the measurements, sends information back. And the point is the computer is blind. It doesn't know the input, nor the processing, and nor the output. This is done in the framework of this measurement-based quantum computing, which is one of the few main avenues how you can build a quantum computer. There's the circuit model where you have gates in here, whereas in this case you make basically this entangled resource state and make measurements basically to process your information. So I will rather shorten that up because Joe gave a nice introduction. Just for curiosity, you might see that experimentalists explain things differently than theoreticians. So we reduced the number of equations and rather work with pictures. So for me, in the simplest way to explain quantum computing is you have these plus states, you entangle them by Cephas operations to a cluster state. You make measurements one by one according to what's shown here on this XY plane. And you see the first plus state is rotated according to the measurement setting, followed by Hadamard to here, and so on. This was done the first time roughly 10 years ago with also 4 qubits. There you can see, depending on the shape of the cluster, one-dimensional cluster, you make 1-qubit rotations. If it's 2-dimensional, you basically get 2-dimensional gates, and so on. And the point is, what I also learned from this blind quantum computing is that very nicely you can split the quantum and the classical part in a way that the quantum part is the entanglement resource, basically the cluster state itself, whereas the structure, 1-dimensional, 2-dimensional, and so on, as well as the measurement settings here, are the classical informations that define the quantum computing. Okay? The point is of the blind quantum protocol is to hide those two informations. To make it short, Brickworks, if you build everything out of bricks, then you can take a snapshot and you don't know what's going to happen because every brick can implement all the ingredients for universal quantum computing. You just need to choose the right measurement settings. So the trick now is how to hide the measurement settings, basically by adding 1 degree of freedom. So now the qubits can have this 1 out of 8 phases, up shown here. The computer makes the cluster state, but doesn't know which kind of cluster state. Makes measurements again. Another point is the computer knows the measurement setting he's doing, this delta, but does not know the phi, which only the client knows. That's the trick. That's the point for making this one blind. In a nutshell, that's how the protocol goes. Now we go to the experiments. Client prepares those qubits with a random phase, sends this to the computer. He makes the entangled state. Computer gets the orders what to measure. He gets results, sends this back. Basically, only you as the client has the benefit to know basically what was done in the computation. So experiments. So when we heard about this protocol, we said yes, that's great. We would like to do it, and then of course comes the first negotiation part. So what's the minimal effort we have to do? Because everything is hard. You know, like we had 4 qubits in our laboratory. We had some constraints with the setup. You know, turnaround is always like 1 year basically with an experiment at least 1 year, maybe sometimes longer. So we could negotiate that actually encoding 2 of them are sufficient to show all the benefits. Yeah? So we could achieve a blind or optimized blind quantum computing by having just theta 2 and theta 3 in the blind configuration. That's the setup. This is where the down conversion source. Here's the client part where we can choose the settings here for those 4 input states. And again, entanglement, quantum computation is happening at beam splitters, optical elements, where the computer makes here the cluster state or the blind cluster state and performs the measurements. I prepared some movie which shows basically this part of the setup in addition of a second gate. So later on we used this part for effectively one C0 and then we added another C0, but that's not so important. That's the picture for the updated setup. The point I'd like to show you what kind of space is needed. So for just this blind quantum computing, that's basically the space for implementing the dedicated quantum computation, and then later on we added this little part for a second C0 gate. It's not so important, but I would rather show you with the clip what I meant, how down conversion works. So what you see now is that's our down conversion crystal. Fast laser shoots through like this blue laser. The pair is either forward or backward emitted. It's a different experiment, so don't be confused about the nomenclature here, but the experimental setup somehow looks the same. So if pairs in one way, we send the laser back, we can send pairs also in that way. Sometimes it happens they come out at the same time, which is what we want to get 4-photon entanglement. We shoot with 80 million shots per second, so you see many photon pairs come out in principle along this way and that way. The tricky part is to align that the single photons overlap coherently at beam splitters. And if one guy is measured, you effectively introduce a gate operation, which is a C0 in that experiment. So after the first C0, the photons continue traveling, go through these wave plates that define the spin state, basically local operations. You see how the spin is changing here? It's cute. And then again, they overlap again with another beam splitter, and I measured at the end for making the final gate. But that's basically what we do for living in the laboratories to make some experiments happening. Okay? No tomatoes.
This picture is also sort of, for instance, you're preparing the cluster state here?
So this is a different experiment we used to. Yeah, that's basically how it goes.
So the cluster state is, I mean, it's sort of flying around.
Yes, precisely, on the table, yeah.
But say, so when you're running this protocol, the server is preparing the cluster state, so it's in these photons.
Yes, yes.
And then at some point it receives some instructions, right? Or
yes. And then it's a very short time script because they fly at the speed of light, literally. So what we do is we... sorry, I interrupted you. Maybe you have a different question.
No, well...
Okay. So of course, here you make you simplify as much as you can. So in principle, you can change shot by shot, but then you have to use very fast switches for doing that. So what we have done is, Alice had one switch, one setting, and then the computer had another setting and made some rounds and collected data. Then in different setting with the other side. So of course, it was not shot by shot. In principle, we should do it shot by shot, but here it was not done like this.
Everything needs to be timed very precisely?
Of course, yeah.
Can you keep the cluster states sort of flying around for a little bit of time?
Yeah. So the setup is very stable that we have. So we can. So once it was aligned and we had our sweet spot, it was running basically weeks. We got data for all possible settings to really measure it until it's dead. Basically to get all the information out we could get from the photon.
On the same state? No,
well, if photons generate, then you measure. So the state itself is basically destroyed because you measure all the time, you know. But you make new ones. Basically, it runs when you make...
So it's not the same photons for the whole week?
No. Of course, they turn into electricity. You know, they get to the APD in the dawn.
Of course.
Okay. Okay.
One question. Did I understand correctly that you don't actually communicate between Alice and Bob, but you let like Alice say what she would communicate and Bob guess what Alice would say, and then you discard the run if it didn't match? Is that essentially what you do?
Don't understand.
So Alice does not actually send to Bob.
She sends the qubit there, okay?
Yeah, but not the classical information. Essentially Bob just guesses what Alice sends, and you, in a sense, discard the experiment if it didn't match up.
No, basically, so it was pre-arranged. Basically, Bob could have got the order to get the classical message what was set, but now we said, okay, for this time we put this setting there, so we added like half a meter of table, so to make here fast communication and speed of light was no point. So we wanted to show that. But in principle, this is what needs to be done.
For example, because in the actual protocol, if you try to scale it, you have like several.
You need these communications, yes.
Then you can't do this.
Yeah, but communication matches some transcript that else would have been.
So, but now we've done it.
Yes, but the probability that the computation will work goes down exponentially.
Yeah, no, but any of them is okay.
Any of what
Could have been.
No, but both today. No, but the point that we could do it. So we have done, basically, we talk about is feed forward and classical communication. We could have done that, and we had actually equipment there. But now we was focusing on the first step towards this story. In the future, we're going to do this. Really like giving orders, implementing feed forward operation, and so on. So this can be done.
So the bob would become bigger and bigger, so that to match the, because between Alice and Bob there's a time that needs to pass.
But you can slow it down. So the tricky part for this, if they go in fibers, they're only 2/3 the speed of light. So you can still have a classical benefit to say, okay, while they're traveling there, you can tell Bob, hey, please be prepared to make this measurement. So this can be done. But you know, this one already took so long to compile. It sounds clear, but to understand how we can implement this in the laboratory took some time, and we said, okay, that's our focus now to do it. And then every overhead is considered, let's do it now. We plan to do it, of course, but at some point you have to decide what's the step you would like to show. Okay, well, that's basically it. So we took our 4 photons and played around in this blind quantum computation scheme. So you see these two were blind, so we could hide 1-qubit rotations. If these two were blind, we could hide those 2-qubit gate operations. And we could implement also like Deutsch algorithm and Grover's search algorithm in a blind fashion. So you see these are the hours of measurement, not for one run, but just to show we took really like all possible settings and we're interested in studying as much as we can of such an interesting computation. Another thing that interestingly I learned from the experiment was that sometimes people ask you, well, we know the theory, like Bell test I heard was also the same case 40 years ago. We know the theory, and the theory seems to be right. Why to bother to make an experiment, okay? And then the thing that we learned, or at least I learned, and I guess maybe Joe and Adam knew already in advance, was that via the experiment itself, and then also from feedback from referees actually, we learned that it's more secure than I thought. And more secure mean that if they have imperfections that we had, you know, computers are not perfect, you have not perfect entanglement generation, then what's basically jeopardized or destroyed is the correctness of the computation, but not the security. So it means the client still can preserve its security, its privacy, as long as if the data are random. I think it was a very interesting thing to learn, that this aspect shows that how strong this protocol actually works in real-life conditions. And with less demanding, I meant that it was shown that by being such a hard negotiator to make it simple for our experiments, that it seems you don't need to make all of the qubits blind. You can find cases or scenarios where you can basically limit the amount of blind qubits, which also is a big benefit in real-life applications. So in the future, we have this kind of dedicated quantum computation. It's my dream to go over distance, and hopefully in the future we can show in Vienna that we can go over some kind of kilometers for this dedicated quantum computation. Okay. That's the obvious thing, security and privacy-preserving features. The thing I was not aware of, which is also like a new baby for me, was the idea of interactive proofs and verification of quantum computations, where this blind quantum computer seems to be a very nice approach, at the moment a very resource-efficient approach to get an idea of what's happening in the machine. It goes back to Dorit and then Oran Eban. That's basically how I heard about the first time about these quantum verification ideas. But since we had this blind quantum computer, we went along this line with Joe and Elham to implement basically this trapped qubits as Joe mentioned. In our case, again, we had 4 qubits, so we had to find some optimized protocol. What we have done is we didn't place the trapped qubit isolated from the others. We rather prepared the trapped qubits by making measurements on those 2, 3, and then we checked, is this result here correct or not correct, basically by comparing what the computer is telling us. And you see we had pretty good results, and see that's real life conditions. So when you get those numbers, 91% success rate, what does it mean? So then comes the hard part for them to say, yes, that's a serious proof. We can show that this is that makes a statement was just noise. But at the end, it turned out it's a pretty good sign. Of course, we placed the trap in different configuration, so we could show in a nice way how this verification idea works. Since it's a small system, we cannot place the traps in a big computation, but rather put it basically like as an alternative run. Either you make a computation if you're 4 qubits, or a verification, and so on. That was the idea of this quantum verification with single photons. Basically, opening the eyes that this is a very interesting concept for getting an idea of what's happening in the machine. We had also debates about what needs to be shown, and there's an interesting difference of opinions. So coming from quantum physics and being like in Vienna with foundations and entanglement and Bell inequalities, we thought that the only way to prove a quantum computer works properly is to make a hidden Bell test, okay, which was a topic also today. But we learned that for computer scientists, sometimes it's even better to make a proof to say, can we trust the machine? Is the machine running properly? And from that, automatically it follows that If it's a quantum computer, you can also do Bell inequalities if you want so, but there seems to be some different opinions about concepts, what's nice to show. Never mind, we showed this kind of blind Bell test where the computer got the input states, he entangled them, he didn't know that he's doing that, and he made also the measurements in a blind fashion, which means he had no idea that he's preparing Bell pairs and making a CHSH inequality within this verification process. Okay, the last 2 minutes would like to raise questions for totally different stories. Now we change gears. And the question is, can we apply verification concepts to this new hype of intermediate or resource-efficient quantum computations? And what I mean by that, let me explain briefly what these resource-efficient computations are about. So Scott basically is the right guy to talk to about the theoretical concepts. It's about Boson sampling, for example. So for that, photons are a very neat system as well. The idea is you can actually very efficiently implement unitary transformations to photons. So if a photon comes in one of those input ports, and you have those complex interferometers where just beam splitters and phase shifters, you can effectively and efficiently map the input state to an output state. So if you modern guide and use waveguides and you have those modes here with beam splitters, and you can adjust to your unitary transformation. So the task is how can you transform your input to an output state. And if you consider the simplest case, which I guess many of you have heard for a couple of times already, it's just a beam splitter where you have a 50% chance the photon comes to be transmitted or reflected. Now you say the task is I put a detector here and there. What's my chance to get a coincidence that those two different output ports we get a click? And then there comes this famous quantum interference effect, also called Hongo-Mandel effect, where you will see that the chance that both photons are transmitted and both are reflected gives you 0, because when you write down the beam splitter matrix, you see that those terms here, the ones A and D, plus those terms here cancel because there's an I phase shift for each photon when it's reflected to the surface. Okay? So this kind of interference effect leads to a very nice feature that this can be explained by the permanent of a matrix. You see there's a plus sign, actually by the permanent squared. And the point is to make it short, it's very hard to calculate permanence. It's a class of sharp P. And what Scott has shown that actually even related things like sampling, which means if a photon comes here and it propagates through, just sampling is very hard because it's related to the permanence within this circuit. So make it short because Scott, I guess, will talk at the last day about this interesting direction. The thing that was so mind-shaking for us experimentalists was that in an ideal case, which is never out there, it's just 20 photons and 400 modes, like as the size of a unitary, in principle would outperform any classical machine. And that's great. I mean, suddenly you see like there's a machine out there or some sample out there, you don't need anything. No 2-qubit gates, basically just photons, which is 20, not so much, and a complex interferometer, which is not that hard and not that unrealistic. So in my eyes, such a concept is among the best, if not the most feasible approach to really set a benchmark. Can be in 15, 20 years from now, see there's a result out there where no classical machine can basically verify this anymore. Okay, which opens the interesting question of the extended Church-Turing thesis, or is there complexity arguments out there that basically would not allow the quantum computers. So for that reason, 4 groups simultaneously jumped on this interesting research. Also, we have done an experiment. So we had these 5 modes. And what's the first non-trivial thing to show? You take 3 photons. Okay, so we had 3 photons in there. This is the real picture of the circuit. We got the output distributions, and the same stuff was done by the groups in Oxford, Andrew White, Brisbane, we've got together, and Fabio Schirino in Rome. Of course, when you have this very nice simple scheme or simple concept to suddenly reach basically outputs which cannot be done by classical computers, how can you be sure that the result is right? Okay, in particular, it's an entirely passive system. It's a passive network, so there are no gates. There's no way to make this kind of interactive proof because there's nothing there. So, and then arises the question: what can be said in a classical way? So, as soon as the papers were out, there were people raising questions. Actually, can you distinguish the output from the Boson sample to a uniform distribution? That was Jens, and then Scott immediately said, yes, of course, read the old paper, was done there already. Okay, that's my way of reading that, yeah. And very nicely, but to the point, look, there's a difference, and then 2 groups basically compared the output when you have interference in the quantum mechanical way and totally classical configurations. We have also done something along this line, but in a more general fashion. We said when we tuned basically the quantumness by changing the distinguishability of the photons, which allows to characterize errors, because there's probably no way of error correction in such a system, because it's passive, no? There's no way to do something. And the question is, which I hope there will be a positive answer, can we extend this problem to bigger classes by considering also permanence, which are immanence, as something we are going to sample. So we have done basically, in a nutshell, because just 2 minutes left, normally we have this kind of situation that 3 photons come in at the same time, so such that they can interfere with and following the rules of the permanent and so on. However, if they're not basically interfering because they have different timing information, so they're not coherently overlapping, then you just get a terminant as a result, which is simple to calculate. However, if they're like slightly overlapping, then you have a mixture of both, which belongs to the class of immanence. And there's interesting open question. Nobody knows yet if the immanence or how many of the immanence are hard to calculate, and if there's basically an interesting open question. But it seems right now, at least that's what we learned from Barry Sanders, that there are interesting hard questions related to immanence. So it might be that there's a more bigger class out there for sampling.
What is immanent?
Immanent basically is a mixture of determinant and so determinant is a minus sign, determinant a plus sign. If you have something which is plus or minus in a different values, then you have immanent. This is the most general case of that. So you have a sign function which changes as you design. Okay. So just learn the determinant and permanent are the extreme cases of immanence. Okay. Okay. Well, okay. So what you've done, basically we changed the timing, the arrival time of photons. If they overlap perfectly, if the permanent case is the spot here, if you change for one of the other photons, you see how you get landscapes, which corresponds to immanence, sampling of immanence of the matrix in there. Okay. Good. With that, I have my last slide. So basically, that's where we are right now with this efficient intermediate quantum computations. So if people ask, why don't you go for much more photons these days? Because I was asked to give some take-home message. What's our challenge? Basically, our quantum computers can be split into 3 parts: source, the circuit, and detections. Recently, there was a huge improvement for detectors. They work very nicely out of almost 100% efficiency if you have superconducting system as here. The ports are also no problem here because you can use, as you like, bulk optics or integrated circuits. But the challenging thing is still to have a good multi-photon source where you get photons with the same properties, with the same characteristics at the same time. And here, all of them are, until these days, probabilistic, which means 2 photons, bright source, 4 photons at the same time. You see on the 200 photons per second. If you go to 6 or 8, you have to wait a very long time to get the positive click and to use them for computations. With that, I have to thank the people who actually did the work. It was not me, but in particular Stephanie Bartz for this blind quantum computing and verification, and Max for this Boson sampling, and then of course the fruitful collaborations with CQT now, Joe, and where is Edinburgh? Here. Elham. There's no particular reason why they ordered like this. No, it's like, I see the look, it's like, kick you afterwards. And here's the summary to show that photons, I think, have benefits compared to other systems because of the capability to be mobile, to fly around. So you can use this for interactive proofs and so on. What are the open questions, which I could come up with, is like, what are the next things to do along the line of experiments for verification, because now we have just made the first step, but what are the obvious loopholes people have to consider? What about avoiding, in principle, classical communication that could happen? What are the next thing? What are the resources we need? Do we need quantum memory? Can we basically go down to really classical communication? So here's the thing, what's interesting to show in the future in experiments. For the quantum works, can we extend this, the interesting intermediate computations to broader class of problems by considering immanence or other degrees of freedom that are changed for this computing? And of course, if you have such a simple device, how can you verify? Or is there some fundamental limit that as soon as it gets too simple, because you have a very simple, very special purpose simulator, or like this Boson sample, is there no way at the end to verify if this interactive proves, because there's a trade-off, no? So that might be an interesting question to see if there's a fundamental reason or limit if this verification of intermediate quantum computations. With that, I reached the end. I hope you could stay in time with your 5 minutes. And I guess now we have time for a few questions and then lunch. Huh?
We can take questions.
So you, in the immanent slide, where you were showing that the determinant was appearing when you have 3 distinguishable photons?
Sorry, let's go. So basically, when the photons are distinguishable, okay? Basically, it's very boring. It's just a classical interferometer. So when they do not overlap. So one photon comes time 1, other one time 2. There's no overlap, no interference happening. Then you get basically results that are related to the determinant of the.
Is that so? I thought with distinguishable photons, I thought it's again a permanent, except now a permanent of a non-negative matrix, a matrix of probabilities.
Yes.
So
yes.
With fermions, you get a determinant.
Yes, it's true. Sorry.
I mean, in both cases, you get something that's easy.
Very easy to calculate. Yeah. Yeah. Sorry, you're right. Yeah. It's different. Yes.
Okay.
But the interesting part was to think of what happens if they're partially overlapping. Okay.
Yeah, no, but I still think this is because I don't know if the immanent here appears in a different means something different. I don't see why you get a determinant and why this is.
So it was my mistake. So it was done. So it's as simple as determinant. Sorry, it's like a permanent. Yeah, you're right. Sorry, because it's the boson, the underlying boson system. You're right. Sorry.
So it's non-negative.
Non-negative permanent. Yeah.
And
but the picture is right. So it was my mistake. It was like the slides are literally made recently. Like, but the main story is this picture here, where you have this. That's the permanent case in the middle where they overlap perfectly, and then you say, okay, what's happening if you consider the realistic noise, that there's some distinguishability from frequency differences, overlapping, and so on, which is happening in real life. Okay, so then you're basically somewhere out in these intermediate regions where you basically have to treat the full picture with immanence and so on.
I mean, I don't doubt that the determinant appears in this case, but I wonder if it's just in a different interpretation. I mean, has a different interpretation than the determinant for fermions.
I agree. It's not we have bosons, of course. There's no fermions in there, but they had this different sign of the permanent, which is then simple to calculate. You're right. Sorry, that was my mistake. Yes.
Just on this topic, could you explain how you? I mean, you have this unitary, right?
Yes.
So how is this? You know, with how do you actually set it into? To get these pictures, how do you send it into an experiment?
Okay, so the unitary is the hard part to calculate. So basically, first characterize the unitary. So you get a chip, and then you make measurements to characterize the unitary. Okay, then you do classically the calculation. What do you expect to see?
Mm-hmm.
So we compare basically. So what you do that is theory. So the theory says, okay, if you know, if you consider these various delays, which was actually the core of the paper with Barry Sanders, we get this landscape, and then we took the data and looked at the end what's coming out, and we made those 6 points and checked are they basically in agreement with the theory. So what you do is you measure basically the output distribution as shown here, which is like theory on one side and experiment on the other side, and you see does this output contribution basically agree with very high reduced chi-squared and so on with the theoretical prediction. So the story of this paper is we would like to understand the realistic conditions when there's like photons are not perfect, there's no delta function, they have a spectrum and so on. And moreover, then we learned that immanence is also hard to calculate, sometimes as hard as permanence, that we can maybe reach a bigger class of computations by playing around with these delays of photons. That's the only story in there.
But if there is no determinant in the distinguishable case, then the partially distinguishable shouldn't be an immanent either, right?
No, sorry. It is an immanent for sure.
Yeah.
It's for sure.
It's an immanent.
Well, it's some more complicated expression that interpolates between this squared permanent of a complex matrix and a permanent of a non-negative matrix. I'm not sure that it is an immanent, but whatever it is, it may well continue to be computationally hard.
Sure.
In the in the regime of partial distinguishability.
How much of the difficulty of generating multi-photon sources is due to getting the timing correct? Or is that not much of a problem?
The timing is not that hard because you have pulsed laser systems, so we're synchronized shot by shot. It's the only painful thing is to wait. Okay, so you have to optimize. You have to optimize to catch as many as possible photons. Okay, and you have two random sources, and you only want to have the case when both emit simultaneously. So here people spend a lot of time to be efficient in coupling, to improve detection, because until these days there's no deterministic photon source. So that's a Nobel Prize in my eyes. If somebody develops a multi-photon source, literally, that's for many applications. If you push a button, they come out like a 5-photon, 10-photon state, you rock. But now, well, there are many approaches, ideas how you can do it, but it's very hard. So nature seems to fight with hand and feet against giving Fock states, basically sharp photon states, for free. That's our challenge.
Right. Let's thank Philip and all the